Hi, this is Bruce, and welcome once again to my Colorado Rocky Mountain lab, where today we're taking a look at a really pristine BK Precision Model 1540 40 megahertz oscilloscope, dual channel. We've got channel 1 and channel 2 here. We have inputs for AC, ground, and DC on both channels. We got position knobs for both channels. We've got modes where we can look at channel 1 alone, look at channel 2 alone, look at both of them together. We can choose to do it in alternate or we can do it in chopped fashion. It depends on whether or not we're looking at slow signals or fast ones. And we have a channel 2 inversion button. Now, right now we only have the one trace on the screen, right? Well, no, that's not quite true. If I invert channel 2 and add, channel 2 wipes out channel 1. And if I put them both back on the screen, they look like one trace. But we can change the amplitude and then separate the traces. And display them both on the screen together. We have 12 positions of vertical volts, selectable volts per division, going from 5 volts to division down to 1 millivolt per division on both channels. The channel 2 position knob also doubles as the X position coordinate adjustment for when you're in the XY mode, which is something that's selectable on the horizontal display. And we'll get into that in a little bit. We have the turn on and off button knob here. And it also lights up the background graticule, which might not be so visible in this strong light, but maybe you can see it. It's not really necessary in this light either because I can see the graticule quite well. We have the probe calibration point, 0.5 volt peak to peak, 1 kilohertz. We'll check that out in a bit. We've got a trace rotation knob. That changes the rotation of the displayed image so that you can make sure that it's flat and matches the graticule exactly. We've got the focus button. Take it from a blur, either way, down to a nice sharp image. And then we've got the intensity button. A lot of intensity available here. Don't need that much. Don't want to do that much. We have, if you pull this intensity button out and then adjust it, it does what they call an astigmatism adjust, which basically makes the image of the dot on the screen more circular or not, and in which case you'll become either sharper or less sharp. All right, so now we go to the horizontal side of things. We have first of all, we can choose the trigger source. Right now we're on channel 1, so I'm using channel 1 signal as my source to trigger both channels, and I'm adjusting my level. I get a stabilized image. We can go to channel 2 as the source of the trigger. We can use an external source, which we haven't got connected, but I'm going right here. We can use the line voltage signal coming in to try and trigger it. But as we can see, the line is not going to be adequate for the frequency that we've chosen. So let's go back. We can go to vertical mode, sort of similar to the problem we had with the line. Okay, we're back to triggering on channel 1 again, and we're doing about 1 microsecond. So we get a signal that makes a complete trace in 1 division, and we're at 1 microsecond. So that means I've got a 1 megahertz signal coming in, which is good because I've got 1 megahertz chosen on this PTS 500 that's inputting the signal over here right now. And if I go to a tenth of a microsecond, then I can adjust my my signal so that I make a complete cycle in 10 divisions. 10 times 0.1 microseconds would be 1 microsecond would be 1,000,000. And to make that more dramatic, we could up the voltage, but since I've got both displayed, we need room to be able to see them. Okay, coupling. We can go AC coupling, which all AC signals are coming in and we're coupling to the trigger that way. We can go high frequency reject. Not a good choice when you're trying to use 1 megahertz as your triggering point. We can go DC coupling, which would incorporate the AC as well as the DC, or we can go what they call frame, video frame, or video line. The common one is the AC. We can go auto, normal, fixed. Fixed, I think, chooses a point that's in between the peaks. And auto, we're able to adjust our level ourselves and get a running signal. You've got a single trigger mode, which is special if you want to trigger just one event. Or we can do the reset for that trigger. Here's our sweep time for the channel A, which is what we're looking at right now. So there we're back to 1 microsecond per division. And then we've got the center knob, and it's like, what's that? Well, this is a B channel. Right now you've got 2 time bases on here. You've got an A time base and a B time base. The A time base is the standard horizontal time base that we're using to display our two signals on the channel 1 and 2. B allows us to do a delayed sweep, and our delayed sweep is something that would allow us to take a look at a portion of the incoming signal, and then we can amplify it up and display it underneath. That's something we'll have to demonstrate. We'll see if we... here's channel 1 on the top, and basically here's the delayed sweep down below at the same speed. So you notice that it looks very much like the top. But if I rotate my my B time base and increase the speed of the time base, then you'll see that it magnifies the waveform. And you'll also notice I'm intensifying a portion of the wave on the incoming channel 1. And it's that intensified portion that I'm displaying down below here and amplifying, magnifying would be the right word. Okay. And I can choose like I've chosen really basically one cycle there. If I adjust the delay time, I can choose what portion of the waveform up above that I'm displaying below. You might wonder, looking at this, what good that is. So we're going to do a couple of demonstrations of other kinds of signals where this becomes an understandable case. So bear with me. We'll set this thing up for some testing. Okay, so we've connected the BK1540 up to this DC voltage standard. It's an analogic AN3100, I think. Maybe it's 31,000, but anyway. This will allow me to dial in any voltage I want from, that would be 100 microvolts up to 1 volt in 100 microvolt increments. So I can provide a lot of different voltages. Like right now, we are on the lowest, most sensitive level, and we are at 1 millivolt. And if I, then if I want, I can dial in a millivolt. Put ourselves on DC. If I dial a millivolt in here, I see I'm up exactly 1 division. And then if I dial in another millivolt, we'll go up more. So we're going to take it through its paces, doing it this way, using the analogic as the DC source, just to show that our vertical circuits are measuring properly throughout the ranges. Okay, so we are at the 1 millivolt per division level. We've checked our ground, found it to be good, and we're at our highest sensitivity right now. We're going to go and apply 1 millivolt. There's 1 millivolt. And we see that we jumped up 1 division. Let's take her back down. 1 millivolt. Here's 2, 3, 4. So that's our most sensitive level. If we go to 2, and let's check our ground. Back to DC. We have 2 millivolts per division. We're up 2 divisions. That would be 4 millivolts. Well, that's what we got, 4 millivolts. There would be 5, 6, 7, 8. So that's working. So we got, and as we climb in our range, we're going to find that we get quieter and quieter. A lot of that's got to do with the noise on the inputs, but also there's noise in the amplifier, so as you get more and more sensitive. Okay, we are 5 millivolts per division, so if I go 10 millivolts, that'd be 2 divisions. And there we go, 2 divisions. Let's go one more. There's 4 divisions. That's 20 millivolts. Right? There's 4 divisions there, times 5 would be 20 millivolts. So that's good. Let's go to 10 millivolts per division. Zeroed. And here'd be 1 division, 2 divisions, 3 divisions, 4 divisions. Going to 20 millivolts per division. Well, we are now at 2 divisions. It makes sense. That would be 80 millivolts. 4 times 20 is 80. Let's try, we're on 20 millivolts per division. And if we go up 10, that's half a division. Here's 20, 30, 40, 50, 60, 70, 80. No problem. 50 millivolts per division. 2 divisions would be a tenth of it would be 100 millivolts, which would be a tenth of a volt. So let's go up a tenth of a volt, and we'll jump 2 divisions. Okay, and then we're another tenth, we'll jump 4 divisions. There we go. So that's working good. Okay, we're on a tenth of a volt per division. So as I go up 1/10, there's a division. 2 tenths, 3 tenths, 4 tenths, no problem. Let's go 2 tenths per division. Okay, if I go up a tenth, that's only half a division. There's a full division, that's 2 tenths, 3 tenths, 4 tenths, 5, 6, 7, 8 tenths. No problem. 0.5 volts per division. Okay. Half a volt per division. 1 volt would be 2 divisions. So let's go 2 divisions. All right. Looks accurate. Let's go 4 divisions. That'd be 2 volts. There's 1 volt in, 2 divisions. 2 volts in, 4 divisions. No problem. Okay, let's go to 1 volt per division. There's 1, 2, 3, 4. No problem. 2 volts per division. There's 1, it's a half a division. 2, 2.5, 3, 3.5, 4, 4.5, 5. Okay. 5 volts per division. Well, I'm only going to be able to push 2 divisions out of here. But let's go 1, 2, 3, 4, 5. That should be 1 division. And we went up 1 division. Here's 6, 7, 8, 9, 10. So we're up 2 divisions. Good. Take her back down. So there we go. We've got all of the scales on channel 1 checked, and they look good. They can definitely read. Okay, so we moved our input to channel 2. We've pushed in the channel 2 button. We are on the most sensitive scale. It's 1 millivolt per division. We're reading 0 right now, and we're going to turn ourselves up 1 millivolt. And we see we jumped up 1 division. Let's take her back down so you can see it. There's 0, 1 division, 2 divisions, 3 divisions, 4 divisions. No problem. I don't know if that helps or not. We'll see. Going to 2 millivolts per division. Make sure we haven't changed. Okay. And we go half a division, well, half a division, 1 division, 1.5, 2 divisions, 3 divisions, 3.5, 4 divisions. So not a problem. We go to 5 millivolts per division. And here's a 10 millivolts, so we're going to jump 2 divisions. And then we jump another 10 millivolts, we're going to jump 4 divisions. There we go. Back down. There we go. Let's go to 10 millivolts per division. Okay, this would be 1, 2, 3, 4. So that's 0.04 volts. And we're reading 0.04 volts up there. 4 times 10 millivolts, it's 40 millivolts, 0.04 volts. Okay, we're going to go to the 20 millivolt per division. Take ourselves back down to 0. Okay. 20 millivolts per division. So here would be a half a division. 1, 1.5, 2, 2.5, 3, 3.5, 4. No problems. 50 millivolts per division. Well, in this case, I'm going to go 100 millivolts. We'll go 2 divisions. And 200 millivolts, we go 4 divisions. So that's no problem. Okay. Let's go to a 100 millivolts per division. There's 1, 2, 3, 400 millivolts, no problem. Okay. We go twice that. This is 200 millivolts per division. So 1 is going to take us up a half a division. Here's 1 division, that's 200 millivolts. 300, 400 millivolts, 500, 600 millivolts, 700, 800 millivolts. Not a problem. Signal is getting a lot cleaner looking. Here's a half volt per division. We're going to use the Yeah, we're going to use the 1 volt per division. We're going to jump up 2 divisions. And we'll go 4 divisions. All right, that's 2 volts. 1 volt, 0. All right, going to 1 volt per division. Here's 1 division, 2 division, 3 division, 4 division. Not a problem. And here's 2 volts per division. We're going to go up a half a division. There's a whole division, that's 2 volts. There's 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, 8 volts. Not a problem. Okay. And finally, 5 volts per division. And 0 looks good. Okay, we can go 2 divisions. We're going to go 1, 2, 3, 4, 5. All right, that's 1 division, that's 5 volts. 6, 7, 8, 9, 10 volts, 2 divisions. 10 volts, going back down to 5. We're at 1 division, taking it down to 0. There's 0, and we're back. Alright, so the channel 2 is also measuring properly on all the ranges. Okay, let's take a look at the horizontal time base right now. Right at the moment, I have myself positioned so that I'm on the 1 microsecond per division on my scale here. And I've got an input, if I follow this line back, coming in from that PTS 500 up there, which currently is measuring 1 megahertz. So I know I've got a megahertz coming in, and I see that I have, if I want to just adjust this a little bit so that I can get it right on the, there. I see that I start a cycle, I go down from the crosshairs, hit my bottom peak, come up, hit my top peak, and come back down right on the line of my first division. So I do a complete cycle in 1 division. And I am at 1 microsecond per division. So I do a complete cycle in 1 microsecond, which would mean that I have to be going 1,000,000 times a second. So that's a megahertz. And it's reading accurately. And if I go and turn my time base from 1 microsecond to 1/10 of a microsecond per division, okay, so we've adjusted ourselves so that we see that we cross right at the center of the crosshairs for the major coordinates. And I'm hitting the left edge of the screen right at the crosshairs, and the same thing on the right. So I'm doing 1 complete cycle in 10 divisions. There's 10 divisions across here. 5 this side of the crosshairs and 5 the other side. Well, if that's 10 divisions, and I'm 0.1 second, according to the scale here, 0.1 seconds per division, then I must have, that would be 1 full microsecond. So if I do 1 full cycle in 1 full microsecond, then I must be running 1,000,000 hertz. Okay. Let's go ahead then. And that means that for my time base, I'm reading good. It would be the same. I'm using the same time base whether I'm using channel 1 or channel 2. But, so I've already proven my point that the time base is good. But if I go to channel 2, and make my trigger source channel 2, and I'm going to see exactly the same thing. I've displayed 1 full cycle in 10 divisions. That's 1 megahertz that I've got to be running if I'm 0.1 microseconds per division and I got 10 divisions. Okay, so my time base seems to be accurate, at least at a megahertz, and I can take her up. Here's 10 megahertz. easily. So I see that I have done one complete cycle in a division, and I am 0.1 microseconds per division, so I've done one complete cycle in 0.1 microseconds. That's 10 megahertz. So I'm displaying one cycle of a 10 megahertz signal for every division. And I can kick her up. Here's 20, 30, 40. Okay, and let's just make it a little easier to see. Oops. Okay, so if I count the number of cycles that I have in a division, what I'm seeing is I go 1, 2, 3, 4. So I've got 4 cycles in a division, and I am running at 0.1 microseconds per division. So that's 4 cycles in 0.1 microseconds. So that must mean I'm running 4 times 10 megahertz. That's 40 megahertz. And that is what I am running, 40 megahertz. So that's the rating of the scope. And if I push in my times 10 up here, I can display a magnified image of that 40 megahertz there. The thing to ask though is, are we 3 dB down at 40 megahertz or less? In order to meet our spec, that would have to be true. So we're going to measure that in a moment. Alright, we've connected ourselves back up to the PTS 500. We are currently putting in a 1 megahertz signal. Okay, so we've got 1 megahertz coming in here, and we've adjusted the amplitude so that we are rising 4 centimeters up, 4 centimeters down for 1 megahertz, which we know is well within the boundary of 40 megahertz. But now what we want to do is we want to measure on this 400 megahertz oscilloscope up here what our amplitude is, and then we're going to match that amplitude when we turn up our frequency to 40 megahertz, and we're going to see what happens on the B and K. So right now I'm going up 4 and down 4 divisions, and I'm just touching the line top and bottom. This is at 1 megahertz with the gain adjusted so that the B and K was full scale. So now what we're going to do is we're going to take this up to 40 megahertz and get a similar looking. Okay, one more. All right, now it looks like we've picked up a little bit of gain when we went to 40 megahertz coming out of this generator. So we're going to adjust the generator amplitude till it just touches the line top and bottom again. Let's see, about like that. Okay, and now we're going to take that amplitude at 40 megahertz. We're going to feed it into this scope. And looks like we're rising 3 divisions and going down 3 divisions. So I know from doing this many times before that if we hit 2.8 divisions out of 4, That's a 3 dB down. We are a little bit better than that. So, we've got 0.2 divisions more, probably somewhere in the order of 5 or 6 megahertz more that we could go and in fact, I guess we could actually do that. Let's just go ahead and see what it would take to hit 2.8. Looks like that's about it right there. So that's about 46 megahertz. And we can double check the amplitude. Make sure it hasn't changed. Actually, it did. Dropped it a little bit. So if I turn it back up to where we just touched the line again, what's going to happen now is I'm going to find out that we still haven't hit 2.8 is my guess. Yeah. We're running about 2.9 right now, so we can go up. So what about there? That's maybe even a little more. Okay, let's see what our amplitude is. Okay, looks like that's about it. And we're running about 2.8 now, so yes. So we're down 3 dB at 49 megahertz. So we beat this 40 megahertz by limitation by 9 megahertz. But we beat the spec. And that's what we wanted to know. Well, lastly, we're set up in the XY position. So I've got my horizontal display switch all the way over to XY. I have a signal coming in from my bench oscillator going into channel 2. That's the X channel, so the width of that pattern is due to channel 2. And in channel 1 I've got coming in from the PTS 500, and it's the Y coordinate, and they're both essentially sine waves. My bench oscillator is not a perfect sine wave, but it's close. And if you are not in sync, then your pattern rotates. If you're way out of frequency, then you get some kind of strange looking patterns showing up, depending on how many times you're off. But if you can get the pattern to stop, like that, that says that the frequency coming into channel 1 and the frequency coming into channel 2 are identical. So you could be taking the frequency from a bench oscillator on channel 2 like I did, and channel 1 could represent the frequency of a crystal that you're adjusting. And as you adjust the frequency of the crystal, if you can get this circle or lobe to stop, to slow down and stop, that's the moment that you have achieved identical frequencies between the two when you're making your adjustment. And it's a great way to do that if you're trying to adjust the frequency, because you get instantaneous feedback. You don't have to wait for a count or anything like that. You can see exactly what's happening. And if that thing stands dead still, you're right on. So there you go. There's XY and an explanation as to how it might be used. I've taken you through the oscilloscope. I've proved that the voltage on the channels is accurate, that the frequencies are accurate on the sweep times. I've demonstrated all of the functions on it, given you some good ideas. It's a beautiful looking unit, and somebody should wind up being a happy person. So happy bidding. Thank you for listening, and see you next time.